Imagine, if you will, stumbling upon a mysterious, incredibly powerful radio pulse. I mean, a flash so bright, it briefly outshines everything else in the sky.
Ah.
Now imagine the truly mind-boggling part. Discovering this burst, this singular energetic whisper, didn't come from some distant galaxy.
Right, not an FRB then.
No, it came from a satellite that's been silently orbiting Earth, dead and decommissioned for nearly 60 years.
60 years, wow.
Yeah, this isn't science fiction, right? It's a real event, and it has astronomers absolutely buzzing. And frankly, I'm thrilled to dive into this cosmic cold case with you.
Yeah, it's definitely got people talking.
So today, we're going to take a deep dive into the astonishing detection of this nanosecond duration radio pulse and the sender, get this, NASA's long-defunct Relay 2 satellite.
It really is like a genuine ghost in the machine scenario.
Yeah.
A signal from, well, not quite the great beyond, but certainly unexpected.
Exactly, from our own orbital backyard, revealing that even the quietest corners of space can hold these explosive secrets.
Indeed, it's a truly remarkable story. So our mission today is to really unpack this surprising event.
Let's do it.
How it was detected, why it was so unexpected, and what it implies, not just for space exploration, but also for our hunt for cosmic mysteries across the universe.
It feels like this intersection of cutting-edge astrophysics, orbital mechanics.
And maybe even a touch of space archaeology, wouldn't you say?
Huh? Yeah, space archaeology. I like that. Okay, let's unpack this then. Our journey begins, as so many do now, with the hunt for fast radio bursts, FRBs.
The usual suspects, so to speak.
Right. Now, for those who might not be familiar, FRBs are these incredibly powerful, enigmatic flashes of electromagnetic radiation. Mostly they're coming from truly distant galaxies, billions of light years away sometimes.
Exactly. And astronomers are constantly scanning, hoping to catch these fleeting signals. They tell us about some really extreme energetic events out there.
And this is precisely what the Australian Square Kilometre Array Pathfinder, ASCAP, is designed to do.
Along with its specialized survey capabilities, the Commensal Real-Time ASCAP Fast Transient Survey, ERAFT.
That's a mouthful.
It is. And its Advanced Coherent Detection System, CRATO. They're built for this kind of rapid detection.
So ASCAP isn't just one big dish. It's more complex than that.
Oh, absolutely. Think of it more like an array of highly sensitive, synchronized ears, each listening to a slightly different patch of sky, all at the same time.
Okay.
It uses this technology called phased array feed technology that lets it form 36 separate, contiguous images on the sky simultaneously.
36 at once. Wow.
Yeah. And what's truly impressive and absolutely crucial for catching something fleeting like an FRB is its ability to process this huge amount of data in near real time.
Right, you need that speed.
You do. It operates across a wide frequency range too. 760.5 megahertz up to 1,000.5 megahertz, and in very fine 1 megahertz channels.
So it's like tuning into hundreds of radio stations at once, but with incredible precision.
That's a good analogy. Precision enough to hear a whisper from across the galaxy, potentially.
And it was exactly this advanced capability that flagged this anomaly. So tell us, what was it about this particular signal? What happened on June 13th, 2024?
Well, the specific time was 05.13.09.035 UTC. At that moment, CRATO detected this unusual burst. It showed up in beam 17 specifically.
Okay.
And what immediately grabbed their attention was its incredibly high signal-to-noise ratio, 16.3.
Which means it was really clear, right? Stood out from the background.
Very clear, very strong. But here's what was fascinating and really the game changer. Most FRB pipelines, the software looking for these things, would typically reject a signal with a low dispersion measure.
Why is that?
Because usually a low dispersion measure means it's probably just terrestrial radio frequency interference, RFI.
Yeah.
Signals from Earth TV stations, radar, mobile phones, that sort of thing.
Ah, so it's like the system has this built-in filter to ignore all the local chatter, basically.
Pretty much. Keeps the system from crying wolf all the time.
But this one still got through. So how did CRATO tell the difference? How did it know this wasn't just, someone's microwave oven?
Well, that's the really ingenious part of CRATO's coherent imaging system. It has much stronger RFI rejection than conventional systems.
How does it do that?
It's based on the wavefront shape. Terrestrial RFI, because it's coming from something relatively close on Earth, has a noticeably curved wavefront by the time it hits the different antennas of the ASCAP array.
Right, like ripples in a pond spreading out.
Exactly.
Yeah.
But a signal from a distant astrophysical source, like an FRB from another galaxy, is so incredibly far away that its wavefront looks essentially flat or planar when it reaches us.
Okay, that makes sense.
And this difference, it's subtle but fundamental, allows CRICO to filter out that ground-based interference much more effectively. It makes it uniquely capable of spotting signals that might otherwise just get tossed out as noise.
So they had this incredibly strong signal, and incredibly brief. You said less than 30 nanoseconds.
That's the total duration, yes. Incredibly brief.
It's hard to even wrap your head around that. A nanosecond is to a second what a second is to, what, over 30 years?
Something like that, yeah. Almost incomprehensibly fast.
But here's where it gets really interesting. Despite how bright it was, the initial analysis, looking at that wavefront shape you mentioned, it indicated it wasn't from a distant galaxy at all. This wasn't some cosmic explosion billions of light years away. It was close, very close to Earth, right here in our cosmic neighborhood.
That's the key. The near-field clue, as the paper calls it, was pivotal.
How did they figure out it was that close, though? What was the specific clue?
When they did the initial offline processing, using another tool called the Celebi pipeline, they noticed something really odd.
Okay.
Only the antennas within the inner 1 kilometer of the array produced a coherent image if they assumed it was a standard far-field source.
Meaning if they tried to use the whole array, assuming it was distant?
The image was blurry, essentially non-existent. But when they restricted the analysis to just those inner antennas within that 1 kilometer baseline,
It snapped into focus.
exactly. It immediately told them the source had to be within the near-field limit of SCOP for that baseline, which for 1 kilometer is about 5,700 kilometers.
Yeah. So right away, that screamed, not an FRB from deep space.
Precisely. It was an immediate red flag. This wasn't extragalactic. This was local. Very local.
Wow. So, okay, it's like finding a super bright flashlight in the dark, only to realize it's practically right in front of your face, not miles down the road.
A good way to put it.
So once they knew it was local, relatively speaking, how did they nail down the distance even more precisely? What did that involve?
That required getting into the really fine details of the signal arrival times. They measured the tiny propagation delay between every single pair of antennas in the array.
Like timing when the sound hits different microphones?
Exactly like that, but with radio waves and much, much higher precision. By timing exactly when the burst arrived at each antenna, they could reconstruct the precise curvature of the wavefront.
And that curvature tells you the distance.
It does. They found time delays of up to 3.4 nanoseconds on the longer baselines, over 3 kilometers. Now, 3.4 nanoseconds is incredibly small, but for these instruments, it's highly significant.
That kind of precision is just, it's remarkable, isn't it? Nanosecond differences across kilometers.
It truly is astounding. And the result, the best fit near-field distance they got from modeling that wavefront was 4,500 kilometers.
4,500 kilometers. And they were pretty confident about that number.
Incredibly confident. The uncertainty was tiny. The root mean square residuals were just 0.075 nanoseconds. That translates to an uncertainty in the distance of only about 80 kilometers, plus or minus 80 kilometers.
So 4,500 kilometers, give or take 80, which, as you said, immediately raises a huge question for any astronomer.
Right. What on Earth, or rather what off Earth, could be 4,500 kilometers away and suddenly let out a powerful nanosecond radio burst like that?
It completely shifts the focus away from the vastness of the cosmos.
And right into our increasingly cluttered orbital backyard.
So with that precise distance, 4,500 kilometers, the search obviously turned to Earth satellites. This is where the orbital detective work really kicked in. How did they sift through? I mean, there must be thousands, tens of thousands of objects up there.
There are. They used publicly available resources, specifically a Python module called Skyfield, which is great for astronomical calculations involving positions and orbits.
Okay.
And crucially, they used the comprehensive two-line element descriptions, TLEs. These are essentially the standard orbital data sets for satellites.
Like a satellite's fingerprint or birth certificate?
Sort of, yeah. They provide highly accurate data on their orbits. They're maintained by NORAD, the North American Aerospace Defense Command, and you can access them via the space-track.org catalog.
So they took the burst's time and sky position
and cross-referenced it against this massive catalog, looking for any known object that was in the right place at the right time at the right distance.
It sounds like searching for a needle in a haystack, but a haystack we have a pretty good map of.
That's a fair way to put it, and the search paid off.
What did they find?
One viable match emerged. It practically jumped out from the data, NORAD ID 737.
And NORAD ID 737 is?
The Relay 2 satellite.
Relay 2. Okay, how close was the match?
At the exact time of the observation, Relay 2 was seen to be within just 3.2 arc minutes of the detected burst position.
Which sounds small, but what does that mean at 4,500 kilometers?
At that distance, 3.2 arc minutes translates to a mere 4 kilometers in the plane of the sky. It's an astonishingly close positional match, practically bullseye.
Wow, 4 kilometers. That's incredibly close. And what about the distance? Did that line up too?
It did, remarkably well. Skyfield also calculated the distance between the ASCAP array and Relay 2 at that precise moment, 322 kilometers.
322 kilometers, and the burst distance was estimated at 4,500 plus or minus 80 kilometers.
Exactly. So 322 kilometers falls perfectly within that range derived from the radio signal itself. The consistency was undeniable.
So you put it all together, the timing, the exact position, the perfectly matching distance.
There's really only one conclusion you can draw. The burst originated from Relay 2.
The evidence seems overwhelming, but, I mean, this is where the story takes that really intriguing, almost unbelievable turn, isn't it? Considering Relay 2's history.
It really is.
For people who haven't heard of it, what was Relay 2? What's its significance?
Relay 2 was a genuine pioneer, a real trailblazer from the early days of the space age. NASA launched it back on January 21st, 1964.
1964, yeah.
It was an experimental telecommunications satellite, one of the very first of its kind, designed to prove you could relay TV signals, phone calls, data across oceans using satellite.
That'll help pave the way for everything we rely on today.
Absolutely. It operated in an elliptical orbit. Perigee, its closest point, was around 2091 kilometers, and apogee, its furthest, about 700 and 411 kilometers, a groundbreaking piece of tech for its time.
A real historical artifact orbiting above us. But here's the kicker, right? The part that just makes this whole thing so bizarre.
Yeah.
NASA officially stopped using Relay 2 on September 26, 1965.
Over a year after launch.
Which is pretty good for the time. But even more critically, its onboard electronics, including its 2 transponders, which, by the way, operated at frequencies way different from this burst.
Completely different bands, yes.
They had completely ceased to function altogether by June 9th, 1967.
That's the key date, June 1967.
So we're talking about a satellite that has been, for all intents and purposes, a dead metal hull orbiting Earth for, what is that? Nearly 60 years?
57 years,
Yeah.
to be precise, between June 67 and June 24, just drifting, silent.
How can something that's been dead for that long suddenly scream like this? It just doesn't compute.
Well, it certainly confirms this wasn't a deliberate transmission. That's absolutely ruled out. A nanosecond pulse just doesn't match any known system on board, especially not from a 1960s design.
And it's not like those zombie satellites we sometimes hear about.
No, this is different. Zombie satellites usually involve an old system randomly powering back on, maybe due to a power fluctuation or a cosmic ray hit, and starting to transmit its old signals again. But this burst is so short, so powerful, it's in a completely different league. Plus, the analysis was meticulous. They looked closely at the data around the main burst, about 0.5 seconds worth. No other significant subpulses were detected, just background noise, consistent with random fluctuations. Nothing suggesting any kind of sustained or renewed operation.
So not a zombie comeback, just one single, powerful, incredibly short flash.
From a satellite that should be completely inert. That's the puzzle.
All right, so we have this powerful, incredibly brief signal from a space ghost, essentially. But what was it saying? I mean, can we learn more by dissecting the signal itself, its anatomy?
Yes, absolutely. The next step was to decode the burst's intrinsic structure. To do that, they had to perform what's called coherent de-dispersion.
De-dispersion, right? You mentioned that earlier. It's like unsmearing the signal.
Exactly. Radio signals, especially when they travel through charged particles like in Earth's ionosphere, get smeared out in time. Higher frequencies arrive a tiny bit faster than lower ones.
Like light through a prism.
And a very good analogy. Dispersion measure, or DM, quantifies this smearing by precisely measuring it and then computationally removing that effect.
You get the signal's true shape, as it was when it left the source.
Precisely. And the best fit DM they found was tiny, 2.26 times 10 to the minus 5 parsecs per cubic centimeter. Or, in units often used for the ionosphere, 69.7 PQ. Total electron content units. And that value, 69.7 TQ, is perfectly consistent with a signal making just a single pass through our planet's ionosphere.
So that confirms it didn't come from deep space. It absolutely nails the local origin.
Absolutely. It's another strong piece of evidence pointing right back at Earth's orbit.
Okay, so they unsmeared the signal. They got its original fingerprint. What did that reveal about how long it lasted and how powerful it really was?
It revealed something truly astonishing. The burst itself, after de-dispersion, consisted of a primary impulse lasting only about 10 nanoseconds,
10 billionths of a second.
followed by some lower intensity structure, bringing the total duration to maybe 30 nanoseconds. But given the limits of the telescope's time resolution, the actual intrinsic pulse could be even shorter, perhaps 3 nanoseconds or even less.
3 nanoseconds. Light travels less than a meter in that time. That's just staggering.
It is blindingly brief.
But also incredibly bright, you said. Put the power into perspective for us.
Immense. The peak power was measured at 1090 times the average background noise level, the off-pulse mean. That resulted in an average flux density across the burst of at least 300 kilojanskis. 300 kiloj.
Kilojanskis. That sounds like a lot.
It is. And here's where it gets even more mind-bending. The researchers suspect the actual peak flux density right at the very sharpest point of the pulse could be much higher, potentially exceeding 3 megajanskis.
3 million Janskis.
Potentially, yes. 3 mj. Just for comparison,
Yeah.
the brightest steady radio sources in the sky are measured in tens or maybe hundreds of Janskis. FRBs are measured in Janskis or tens of Janskis, but they last milliseconds. This is potentially megajanskis, but for nanoseconds.
So how much power would Relay 2 itself have needed to generate to create something that bright from 4,500 kilometers away?
Okay, let's translate that. Assuming that 3 mj peak value over the observed bandwidth, that corresponds to an incident power hitting the telescope of about 10-11 watts per square meter.
Tiny amount hitting us, but it came from far away.
Right. So working backwards at a distance of 4,500 kilometers, that implies the source produced an electric field strength right at the satellite of about 280 volts per meter.
280 VOM. Okay.
And if you assume, reasonably, that this emission radiated outwards into about half the sky 2 pi steradians is the technical term?
Like a wide flashlight beam?
Sort of.
Yeah.
Then this translates to a peak power output from Relay 2 of around 400 watts.
400 watts for just 3 nanoseconds.
Yes. An immense amount of energy released in an incredibly short burst from something that's supposed to be completely inert. It's like an incredibly bright, incredibly fast camera flash going off in orbit.
Wow. Okay. Now let's get to the polarization puzzle, because you hinted this is where things get really weird and challenge the explanations. What did the polarization tell them?
Right. Polarization tells us about the orientation of the radio wave's electric field. First, they measured the rotation measure, the RM. It was negative 2.14 radians per square meter.
And that matched expectations.
Yes, that value is perfectly consistent with models of the Earth's ionosphere, further confirming the local origin. So that part fits.
Okay.
But the polarization properties were fascinating. At most frequencies across the band, the burst was purely linearly polarized.
Meaning the waves were vibrating just back and forth in a single plane.
Exactly. Which, interestingly, is something you might expect from certain types of electrical discharges. So far, so good, maybe.
Okay. That seems to fit one potential theory then, but you said there was a twist.
A really unexpected one. The signal suddenly shifted to being 100% circularly polarized at 2 distinct separate parts of the frequency band, one near 800 megahertz and another near 1 gigahertz.
Circularly polarized, so instead of vibrating in a plane, the waves were rotating, like a corkscrew.
Precisely. It's a fundamentally different polarization state. And it wasn't just a little bit circular, it was fully 100% circular in those specific frequency slices.
But linear elsewhere.
Mostly linear elsewhere, yes. When they averaged it all out over the whole burst duration and frequency band, it came out as 75% polarized overall. But that hides this really strange frequency-dependent switch between linear and circular polarization.
That is weird. Why would it do that?
That's the million-dollar question. This specific complex polarization signature shifting from linear to fully circular at distinct frequencies is a key detail, and it poses a significant challenge to fully explain with our current models of what might have caused this burst.
So it suggests whatever happened wasn't just a simple spark. There's some complex physics going on that we don't quite grasp yet.
Exactly. It's a clue that something more intricate is happening during the energy release process. It's perhaps the most mysterious aspect of the whole discovery.
Okay, so armed with all these incredible details, the speed, the brightness, the local origin, and this really peculiar twisting polarization. Let's get to the suspects. What could possibly cause this?
Right. Theory number 1, electrostatic discharge, or ESD.
ESD. We've touched on this before, but let's recap. It's basically like static electricity in space.
That's a good starting point.
Yeah.
Think about scuffing your feet on a carpet and getting a shock from a doorknob. Now, imagine that happening on a satellite.
Okay.
Spacecraft in orbit are constantly bathed in the space environment. Charged particles, electrons, ions, solar radiation. They can accumulate charge, especially as they pass between sunlight and shadow, or through different regions of plasma.
And this builds up.
It can build up significant voltage differences, either between different parts of the satellite surface, if some parts are insulating and others conductive, or between the satellite as a whole and the plasma surrounding it. Until the voltage gets too high to hold in ZAP. A sudden electrostatic discharge occurs. An arc current flows, releasing that built-up energy in a flash.
And this is a real problem for operating satellites, not just theory.
Oh, absolutely. ESD is a well-known hazard. Can cause phantom commands, damage sensitive electronics, degrade solar panels and surfaces. It's a serious concern.
Have we seen examples?
Definitely. There was the temporary loss of the Galaxy 15 communications satellite back in 2010, widely attributed to an ESD event that scrambled its systems. And there's ongoing research suggesting ESD contributes to the gradual degradation of GPS solar arrays over time.
So engineers try to design against it.
They do. Modern spacecraft use conductive coatings, careful grounding strategies, things like that, to try and prevent charge from building up or to dissipate it safely. But it remains a risk. And importantly, most satellites don't have dedicated sensors on board to monitor this charge buildup or detect the discharges directly.
So we usually only know if something goes wrong, which is where remote sensing comes in. Can we hear these sparks from Earth?
People have certainly tried, and succeeded to some extent. Lab experiments back in the 80s showed ESD could produce radio bursts. And more recently, the Arecibo telescope actually detected radio emission around 350 megahertz from operational GPS satellites.
Really? What were those like?
They typically last about 40 to 50 microseconds, much longer than our nanosecond burst, and had a peak flux density equivalent to about 3,000 Janskis if they were at a standard distance. So we know satellites can spark, and we can sometimes detect it.
Okay, so this Relay 2 burst, it shares some features with those Arecibo GPS bursts, right? Like a similar pulse shape with a secondary peak.
It does, which is suggestive. But the Relay 2 burst is way more powerful. If you took one of those GPS satellite bursts detected by Arecibo and imagined it happening at Relay 2's distance of 4,300 kilometers, it would only appear as about 65 kilojanskis.
Compared to the 300 kiloj average or potentially megajansky peak from Relay 2, that's a big difference.
A huge difference in power. So why would Relay 2's spark be so much stronger?
Maybe because it's so old.
That's a very plausible idea. Being a very early spacecraft, launched in '64, Relay 2 was likely built with different materials than modern satellites. Perhaps some materials with higher resistivity, meaning they insulate better and can therefore hold much more charge before discharging. Or maybe different dielectric properties.
Like a bigger capacitor, essentially. Builds up more energy before it lets go.
That's the concept, yes. More stored energy could lead to a more powerful discharge.
But what about the duration? That's the other massive difference. The Arecibo bursts were microseconds. This was nanoseconds, 1,000 times shorter.
That is the most striking difference, and honestly, a bit puzzling for the ESD model. While some lab experiments looking at arcs from dielectric materials have shown very fast rise times, around 3 nanoseconds, and total durations maybe 10 nanoseconds, producing such a brief pulse at these relatively high gigahertz frequencies is still somewhat unexpected based on previous observations like Arecibo's.
So the power difference might be explainable by age, but the extreme brevity is harder to fit.
It's less commonly observed, let's say. However, a huge plus for the ESD theory is that it works perfectly well for a decommissioned satellite. It doesn't need the satellite to be operational. It's just physics happening on the inert structure.
Right. It's just charge building up and releasing.
Exactly. And intriguingly, they checked, and there was no specific trigger event at the time, no big solar flare, no geomagnetic storm, nothing obvious that would cause a sudden charging event.
Which suggests...
It suggests that maybe these kinds of bursts from Relay 2 are just normal occurrences, perhaps happening regularly under standard space weather conditions, just releasing built-up charge periodically. We just happen to be looking at the right time with the right instrument.
Okay, so ESD is a strong contender. Plausible mechanism, works for a dead satellite, maybe explains the power, though the duration is a bit extreme. What's theory 2?
Theory 2, a micrometeoroid impact.
Getting hit by a tiny bit of space dust.
Essentially, yes. Space is full of tiny particles, micrometeoroids, bits of dust and rock, often no bigger than a grain of sand. But they're traveling incredibly fast, tens of kilometers per second relative to the satellite.
Hypervelocity impacts.
Exactly. When one of these hits a spacecraft's surface, the impact is so energetic it instantly vaporizes the particle and a tiny bit of the spacecraft's surface, creating a rapidly expanding cloud of plasma.
Plasma, superheated, ionized gas.
Right. And this plasma cloud can do a couple of things. It can interact with the spacecraft's existing charge state, maybe triggering a discharge, or the rapidly expanding plasma itself, being conductive and moving through magnetic fields, could directly generate radio frequency emissions.
Have they seen this in the lab too, like the ESD experiments?
They have. Lab experiments simulating hypervelocity impacts have detected very short radio pulses, some as brief as 2 nanoseconds.
Okay, that matches the duration.
It does match the time scale well. Those pulses were thought to be caused by discharges occurring across microscopic cracks formed in the target material by the impact. However, one slight difference is that those lab pulses often occurred in groups or bursts, not as a single isolated event like the Relay 2 signal.
Okay. A point against it, maybe?
A slight wrinkle. Other studies looking at impact plasma found the emission was strongest at very low frequencies, down around 1 kilohertz. But importantly, they also noted the presence of very narrow spikes within that emission, much less than 100 nanoseconds wide.
Which implies?
It implies that higher frequency emission, potentially up in ASCAP's observing band around 1 gigahertz, is also possible, even if the bulk of the energy goes into lower frequencies. So it doesn't rule it out.
Okay, so the physics seems plausible, but could a tiny impact actually generate that much power? 400 watts peak.
It seems surprisingly possible. Hydrodynamic simulations, computer models of these impacts, suggest that even incredibly small impactors could produce significant electric fields.
How small are we talking?
One estimate in the paper suggests an impactor weighing only about 22 micrograms.
Micrograms, that's minuscule. Like what, a single eyelash?
Roughly that mass, yes. An impactor that small, hitting at typical orbital speeds, could potentially have generated the observed electric field strength of 280 volts per meter.
An eyelash hitting Relay 2 causes a 400-watt nanosecond radio burst. That's wild.
It highlights the immense energies involved in hypervelocity impacts. But then the question is, how likely is such an impact? Are satellites getting hit by eyelash mass things often?
Yeah, what are the odds?
Well, based on the estimated flux of micrometeoroids of that size in Earth orbit, the researchers calculated the probability. For a satellite like Relay 2 being within ASCAP's field of view, the chance of it suffering an impact capable of producing this signal was about 1.7% over the 100.5 days of observation accumulated by the TFFT survey up to that point.
1.7%. So not common, but definitely not impossible. Statistically plausible, you'd say?
Statistically plausible, yes. It's a low probability event, but given enough observation time, you expect to see one eventually.
So we have two strong contenders. ESD may be favored by the similarity to GPS bursts in the old satellite materials, but with a question mark over the duration. And micrometeoroid impact, which matches the duration better, perhaps, is statistically plausible, but maybe less likely to be a single pulse and needs a tiny impactor to do a lot of work. Where did the researchers land?
The paper leans, maybe slightly, towards the electrostatic discharge scenario.
Why?
Mainly because of those similarities with the previous Arecibo detections from GPS satellites. Even though the power and duration are different, the pulse-shape similarity is suggestive. And the idea that older satellites might just be prone to larger discharges seems physically reasonable. It feels like a more intrinsic process for the satellite.
Okay. But it feels like there's still a piece missing, right? You mentioned the polarization.
Exactly. That's the lingering mystery that neither the simple ESD model nor the simple micrometeoroid impact model, as currently understood, fully explains.
That weird switch from linear to 100% circular polarization at specific frequencies?
Precisely. While you can argue that electrical discharges might produce linear polarization, getting that abrupt shift to perfect circular polarization and only in specific narrow frequency bands near 800 megahertz and 1 gigahertz, that's the part that really stands out as unexplained.
So what does that imply? What keeps the scientists scratching their heads?
It implies there's some additional physics at play. Maybe the discharge isn't just a simple arc, but interacts with the satellite's structure or the local plasma environment in a complex way that generates these specific polarization effects. Or maybe the impact plasma physics is more complex than current models capture. It raises the question, what new mechanism or refinement to existing models is needed here?
It tells us we're potentially looking at something fundamentally new about how these energy releases happen in orbit.
That's the exciting part for the physicists involved. It's not just identifying the cause, but potentially uncovering new processes.
Which really brings us to the bigger picture. Why does this discovery matter? What are the implications beyond just solving this one satellite's spooky signal?
Well, let's start with spacecraft safety and this idea of remote sensing.
Right. This Relay 2 spark wasn't just a curiosity, it highlights a real-world issue. ESD is a genuine threat to operational spacecraft.
Absolutely. These discharges can cause subtle damage, gradual degradation of performance, or even sudden mission-threatening failures. As we rely more and more on satellites for communications, navigation, weather, science, ensuring their longevity and reliability is critical. Understanding all the ways they can fail, including ESD, is vital.
And this discovery suggests a new way to monitor that threat.
Potentially, yes. As we said, most satellites can't monitor their own charge state or detect ESD events directly. So the ability to remotely sense these discharges from Earth using radio telescopes opens up a powerful new possibility.
Like giving satellites a health checkup from the ground, listening for sparks.
Exactly. Imagine being able to monitor a fleet of satellites, listening for the rate or intensity of these discharges, and maybe using that information to assess their health, predict potential problems, or even understand which orbital environments are harsher.
It's repurposing tools built for looking outwards, to look inwards at our own technology.
Precisely. It shows how techniques developed for fundamental astrophysics, for hunting FRBs from across the universe, can be turned around to help us manage our immediate space environment much better. It's a fantastic example of cross-disciplinary application.
You can imagine retrofitting existing experiments or even building dedicated instruments just to listen for these satellite sparks. A whole new field of orbital monitoring.
It's certainly a possibility that this discovery brings to the forefront. But there are implications for astrophysics too, and it's a bit of a double-edged sword.
How so?
Well, on one hand, these nanosecond-scale radio impulses are exactly the kind of signals that some other astrophysics experiments are looking for. Specifically, those searching for faint radio flashes produced when ultra-high-energy cosmic rays or neutrinos interact with the moon or ice sheets or even the Earth's atmosphere.
Ah, so these satellite bursts could look just like those cosmic signals.
They could. They might become a new source of false positives, radio frequency interference, or RFI, that these experiments will need to carefully identify and filter out. These satellite sparks could be cosmic imposters, essentially.
Making the search for those rare cosmic signals even harder.
It adds another layer of complexity, yes. We need algorithms smart enough to tell the difference between a spark from a nearby satellite and a potential signal from a cosmic ray interaction millions or billions of light years away, or hitting the moon.
But you said it was a double-edged sword. What's the flip side?
The flip side is that the very experiments looking for those cosmic signals might be perfectly suited to studying these satellite bursts.
Ah, turn the problem into an opportunity.
Exactly. Existing astroparticle experiments like LOFAR in Europe or the Auger Engineering Radio Array in Argentina, they already operate at lower frequencies, 1000 megahertz, but on nanosecond timescales. They could potentially be modified or their data reanalyzed to specifically identify and study these spaceborne impulsive events.
And not just them.
No, many of the instruments searching for FRBs in the higher frequency range, 400 megahertz to 1.5 gigahertz, like ASCAP itself, or CHIME in Canada, and others, they could also be retrofitted or have their search pipelines adjusted for this new purpose.
So you could end up with a whole network of telescopes capable of doing this.
You could potentially build up a systematic campaign, observing large numbers of spacecraft across different orbits, different ages, different types, and really start to build an unprecedented understanding of how often these events happen, what triggers them, and maybe even finally nail down that peculiar polarization signature.
It's fascinating how a source of interference can become a whole new field of scientific study, listening to the secret active life of dead space junk.
It really is. It reveals hidden dynamics in an environment we thought we understood, or at least an environment we thought was mostly passive when it came to old hardware.
So let's recap. What started as a routine search for exotic signals from the distant universe
led us instead to this surprising, incredibly energetic pulse from a satellite that's been dead for over half a century, NASA's Relay 2.
We've explored how these incredibly advanced radio telescopes, designed to catch whispers from across the cosmos, managed to pick up this nanosecond burst.
And how meticulous analysis using the signal's wavefront curvature and precise timing traced it back definitively to its origin, 4,500 kilometers away, right where Relay 2 was orbiting.
We looked at the two main suspects. A sudden electrostatic discharge, ESD, basically Space static electricity buildup.
perhaps amplified by the satellite's old construction materials.
Yeah.
And the alternative, a hypervelocity impact from a tiny micrometeoroid, an eyelash-sized speck hitting at orbital speeds.
Well, the exact trigger, and especially that really weird shifting polarization signature, remain open questions, a genuinely fascinating mystery.
The implications are definitely profound. This isn't just a scientific curiosity. It highlights a real threat to operational spacecraft ESD, but also points to a potentially powerful new way to monitor satellite health remotely.
It really does make you think. This whole deep dive reminds us that even in the vastness of space, and maybe especially in the crowded orbits closer to home, there are still these surprising mysteries to uncover, even from our oldest, most silent sentinels.
It's true. Objects we dismissed as inert junk might still have stories to tell, if we listen in the right way.
Could this discovery really kickstart a whole new field, like space archaeology via radio astronomy, allowing us to remotely listen in on the hidden life or maybe the unexpected discharges of these long-lost orbital relics?
It certainly opens the door to thinking about orbital debris and defunct satellites, not just as passive hazards, but as potentially active objects emitting detectable signals, revealing ongoing physical processes.
It makes you wonder, what other dead objects are out there, silently signaling in ways we haven't noticed yet? What other secrets are orbiting above us, just waiting for us to tune in and listen closely enough with perhaps these new radio ears?
It suggests there's likely more to be found. We just needed the right tools and perhaps the right accidental discovery to point the way.